Today we're going to go over optimization. Optimization is very common on the AP exam or on any calculus final exams in college. Optimization problems are at first glance seem very difficult because of the amount of words and what the heck is going on. But today's goal is we're going to go step by step through a simple problem, which hopefully will make it easier for you in the future. So let's get right into it. Find the dimensions of a rectangle with the maximum area that can be drawn in the curve y is equal to 12 minus x squared above the x-axis. So, step one, what is going on, right? Let's understand the problem, right? Let's just understand what is going on. So, we are trying to draw a rectangle with the maximum area under a curve. So, let's break it down. Finding the area of rectangle, we know that is, so area of rectangle is just, width times height, right? Or length times width. Now, let's draw out this curve. I went ahead and went to Desmos and kind of took a little screenshot of what that curve is. Please don't make fun of me not being logged in. I actually don't have an account in Desmos, but whatever. So we are trying to find the biggest rectangle area under this curve right here and above the x-axis. So within this dome looking shape, right? So first thing we see is that let's try to relate it to problems of area of a rectangle, right? We're trying to make a area of a rectangle. So we see that the width, right? This is your width, and this is your height. So we see that the width goes, so x, we're going to say is here. So from the y-axis to your curve, right? And all the way down. So x changes. And then we have x on the other side like this, right? So we're going to say your width is just equal to 2x. The reason I put a 2 is because it goes both directions, so like that. Now let's do the height. And it's 2x just because x, right, in a square, x is just one side, right? So we're going to have y to be that part. But now y also varies quite significantly, right? There's a curve to it. So to find y, we are already given the curve right here. So let's just write that out. So we'll have y is equal to 12 minus x, right? So we have your width and we have our height, right? This is our height. So now let's plug these into the area function. So we have area is equal to width times height, and that is just equal to 2x times 12 minus x squared. Oh, sorry, this is squared. All right. Now let's simplify this, make it a bit easier on the eyes. This comes down to be 24x minus 2x cubed. All right. So once we understand the problem, we've drawn it, we've understand how we relate it to what we were looking for. Step 2 becomes solve. Quite simple. So let's take the derivative of this, right? Because we want to maximize the area and we need to, the area changes, right? So there is a change in height. So there's a rate of change. And whenever there is a change, we take a derivative. So let's take the derivative of both sides. So we're going to get dA dx, right? And it's dA because we are taking the derivative of a with respect to x. X is this part right here, right? We want to know the change in height over the change in width. So that is why it's dA over dx. And this is equal to 24 times dx over dx, which we can just cross out, minus 6x squared times dx over dx, which we can cross out. You don't have to write these two dx over dx's. I'm just writing it to kind of get it in your brain that whenever you take a derivative, you always multiply it by d times the variable, or d variable that you're taking the derivative of over d variable with respect to which the derivative is taken. So rewriting this, we have dA dx is equal to 24 minus 6x squared. And to maximize the area, we take the derivative and we set it equal to 0, right? We don't want there to be any more change to the area which we were finding. We want to find the maximum. So it's changing all the way to the max, stop it. So we're going to say, with respect to 0, we want to find our critical points. That's another way of saying it. Probably should have started with that. My bad, guys. So to solve for your critical points, we'll have 6x squared is equal to 24. X squared is equal to 4. X is equal to plus or minus 2. So our critical point on this graph is plus or minus 2. These are our critical points. That is the point of which we can make the biggest rectangle in this chart, right? But that is only for x, right? So we found our x. So let's plug it back into our width. Let's go into the width part. And we know that width is just 2x. So we're going to say 2x, right, which can just be 4 because we found that x is 2. All right, now let's go to the height. Right, so width is 4, which again should make sense because our critical points goes from negative 2 to 2, so the distance between them is 4. That's our width. Now let's go to height. Height, again, is given by 12 minus x squared, right? Yeah, right here. And now we know x, so we can just plug that in. We know x is 2, so this will be 12 minus 2 squared is equal to 12 minus 4, which is just 8. So the height is 8, and the width is 4. Sorry, not this, 4. So that means, going back to this rectangle, the biggest that we can draw is 4 on your height. Oh, my bad, I'm sorry. 4 on the width, 8 on the height. This is supposed to be an 8. And that is the biggest rectangle that we can fit within that curve. So the key to optimization problems is always write the function to optimize, right? In this case, we're lucky we're given the function. Take the derivative, set it equal to 0, right, to find critical points. And then plug whatever you find, your variables, back into your original equations. And that is how you optimize every single problem.